This is a way to share the kinds of work that we do on ECSS projects. It's pretty varied. It gives the other ECSSers, we've got about 70 of us across 9 different sites, a way of keeping on top of what one another is doing on these projects. We also tend to have a lot of campus champions join these calls too, which is really terrific. And we've got some diverse talks for you today. So Mitch Horton from NICS is going to be speaking first about his work with, and actually JUNQI Yin's work with Professor Yang Zeng at the University of Missouri at Kansas City. And it's kind of a high frequency trading project, which is really interesting. And we've been seeing an increasing number of these on Exceed. So definitely a move past the traditional differential equations, physics, engineering types of projects to see some more diversity. So I'm really interested to hear how this relates to some of the other projects that we've seen in this way in Exceed. So I think with that, I'll let you take it away, Mitch, and go ahead and introduce the project.
Thank you, Nancy. I'm Mitch Horton. I work for ACE, which is was established by Joint Institute for Computational Sciences, JICS. And I want to point out in the beginning that this is a project that I only just took over, just a few short weeks ago, and haven't really had time to do anything except come up to speed on it, although I am a seasoned CUDA developer and a seasoned PHY developer. I've got 7 years of experience on accelerators, and so it makes sense to me what JUNQI did. I had to struggle a little bit to come up to speed on the app, but I can present it at a very high level, and I think everyone will understand what's going on here. But just to point out, the work I'm presenting was done by JUNQI. He's the guy that did this work. I don't want to sound like I'm claiming any credit. All I did was come up to speed on it, and I was happy to have this opportunity to present this. And so that's where we're at. This is a statistical analysis for partially observed Markov processes with mark point process observation. What that means is it's a financial app. And it's a financial app that was written in Fortran, and the one major point of this project was to accelerate that code using CUDA, and also to distribute it using MPI. As we go forward, I'll explain how there are also some new features that were added along the way. So the way this is stated in the literature, the particle Markov chain Monte Carlo PMCMC method is applied to estimate ultra high frequency data models in which the underlying intrinsic value process follows a geometric Brownian motion or Heston stochastic volatility model. The point is, you can use any stochastic process you want, and the PI of the project already had geometric Brownian motion code working before we came, and part of this project was to add the HSV code to it, and the 1/8 and 100 kit size rules means that those are the prices you have to trade at. You can't trade at 1/2 of a penny. And then this last sentence says that it's shown that the PMCMC method is able to yield reasonable estimates for model parameters. So you have this geometric Brownian motion model or the Heston stochastic volatility model, and you also have you have a parameter for the noise model, and those are the parameters that we're trying to estimate. So we have two models for streaming financial ultra-high frequency data. For each model, there are unknown parameters. For each model, we have two methods for estimating unknown parameters. We evaluate at the 1/8 100 tick mark size. And for each solution, there are three versions: Fortran accelerated using GPU, and Fortran accelerated using multiple GPUs. The reason why there's two methods for estimating unknown parameters is because before we came along, the PI had a very good method for calculating an estimation for the parameters, but it turned out that it was so complicated. A Monte Carlo Markov chain turned out to be a lot more efficient. And the point of this slide is that PI's models do consider the explicit structure of market microstructure noise, and we'll go over that on another slide, exactly what that means. This slide just shows what the geometric Brownian motion model is, and if you look here, there's a mu parameter and a sigma parameter. Those are two of the three parameters that this model estimates for the geometric Brownian motion. And then for the Hessian stochastic totality model, it also has a mu and a sigma, and it has this parameter and that parameter, and that's it for this one. The way people talk about the estimation method that this code had before we got started is that it's a Bayesian filtering estimation method. The method is a recursive algorithm relying on the Markov chain approximation method to compute the approximate posterior and then the Bayes estimator. And that's a calculation. This second method, the particle Markov chain Monte Carlo, it's a sampling problem. And I guess I worked on a project once before where we did this kind of thing. It was a phylogenetics code, and you have a bunch of aligned sequences that you pulled out of someone's body because you're studying the hepatitis C virus. They all mutated since that person got the virus. You consider those to be the leaves of a tree, and you want to find out what the parent looks like, and so you want to make all possible trees, but you can't. Because if you have a tree, you can figure out its probability because you know the probability. You have a model for the probability that each nucleotide might mutate to another nucleotide. So you can figure out the probability of a given tree, but you can't make them all, not before the sun goes supernova. So you just make any random tree, then you change it randomly and accept it or reject it intelligently, and then do it again 400 million times. And the tree that you visit the most times is the tree that is the most probable tree. And we do that same kind of thing in this project. And this slide talks about the intuition of what's going on here. The model is based on the intuition that trading price should arise from an intrinsic price process in combination with market noise from trading activities at trading times. The model consists of three parts: trading time series, microstructure noise, and observed price, and unobservable intrinsic process. To break that down, the trading times are not regular. I'll show you the model for generating the trading times. They're random. And what you do is you have an intrinsic value, the price of the stock that you generate from the model, and then you add the noise to that to come up with the actual price, and in the end you pull out the right parameters for the model because you've tuned it. And this shows about the trading times. The trading times are modeled as a time series. It's a doubly stochastic Poisson process, including the Poisson process with constant intensity. And then the market microstructure noise. What I was reading in the literature is a lot of people don't model this. A lot of people model it with just white noise, and both of those things give very poor results in certain conditions. This gives a little better results. Discrete noise means that the prices can only move in reality discretely. The the smallest tick size for trading is set by the security exchange, your model might not come up with that. Your stochastic model for the intrinsic price won't land on the tick mark necessarily. So you have to add something to it, and that's the noise. Clustering noise means that people don't necessarily favor one tick mark over another. They might value a round dollar price more than not a round dollar price, or a half dollar price more than a quarter dollar price. That's what the number 2 means. And the third source of noise is everything else. This shows how the noise is calculated. This first line says this S of T sub I is it's the price you generated from your model, the intrinsic price. And for each value, you round it first. That's step 1 right here. And then you incorporate this non-clustering noise, where D is a random variable independent of the intrinsic value S of T, and we use a W geometric distribution with parameter rho and M equals 100. This rho is the other parameter that the model estimates, and that's it for the parameters that we're estimating. And then 3 is another sort of a model. We incorporate clustering noise by biasing the current price. It's Y prime of T sub I, and it just means you have two parameters, alpha and beta, that are fixed, and they move the price to some close tick mark according to what the model says to do. And what I'm doing here is to kind of show you that this project is in its latter stages. It's almost done. There's been a lot of good work done, and these next few slides are a quick snapshot of the most recent fiscal year. I don't mean fiscal year, I mean starting in June of 2015 through June of 2016 plus an extension. So in the first quarter, starting July 1st, there was an effort to try the code on real data as opposed to simulated data. And that involves some pre-processing. You have to trim the end and the beginning, and you have to get rid of outliers. And then somebody had to write a checkpoint mechanism for the NPI CUDA code because it was taking longer than 24 hours, which is all that we were given on Beacon. Quarter after that, that's when we implemented the new algorithm, which was the HSD and the particle filtering via simulations. And first thing we did, or JUNQI did, was refit that back into the GBM model to make sure it worked. And after that worked, he applied it to the new model, HSV. And the interesting thing in this slide is that just things got tested, things were working, new code was written, and this shows that multi-GPU code was shown to scale well, and that means on a single node, I think. And this note just states that that the CU RAND library was used. If you're writing CUDA code and you have an opportunity to use one of the libraries like cuBLOS or CUFFT or CU sparse, in general, you get much better performance than if you write it yourself. The caveat to that is if you've got 6 months, you can always beat NVIDIA's code. That's because they don't have a person sitting there dedicated to solve your problem only and have 6 months to do it. And that's it for the slides, but I did want to go through one thing. I had just enough time to stream through the code, and I wanted to point out just what I thought was one interesting fact.
Yeah, Mitch, we also had a question come in about kind of the larger question that the PI was investigating in this work.
It's sometimes people say that they're using these models to judge the volatility of the market. And this is not my area, and so I can't really speak to exactly what that means. But you want your model to match the actual data. I believe if your model matches what actually, if it can model, if you tune the parameters correctly, then your model with the tuned parameters should, given the same starting conditions, move just like the real data did over the past. Given that, maybe you have a good thing to predict the future. That's my sense of it.
Yeah, I was going to ask about model validation. That's pretty interesting.
And what you want to do with this, I've come to find out, is not always the same thing. But the biggest thing I hear people say is they want to know about an asset's volatility, because that affects more than anything else whether or not it's a good trade.
Yeah, I think in the previous ECSS project, the PI was Mao Ye out of U of Illinois, Urbana-Champaign, and I think they were looking at the impact that the high-frequency trades had on the market in general. And as I recall, that one led to actual changes in how the Securities Exchange Commission regulated things. So I think you're right, Mitch. This gets used for an awful lot of different things, whether it's valuing investments. Or
the key word in this PI's work, the key phrase is market volatility and asset volatility. He wants to either, I think if you don't know the asset's volatility, that's bad, or maybe if it's extremely volatile, that makes it a bad trade. And so, any more questions?
No more at this time. Thank you.
Okay, well, I just wanted to stream through this code. It's and I'm only just pointing out one thing, and maybe everyone on the phone is a seasoned CUDA programmer, and if so, I apologize. I'm just showing what you have to put a set device call around before you do it when you have more than one device. So you have a node and you have maybe 4 GPUs, and you're running an executable. That executable can do things against any of the GPUs. And so this is the code. You see, if you can see this yellow right here, this is a CUDA set device. There memory is being allocated. You have to allocate the memory on one device or another. If you allocated all the memory on without doing this set device, it would all be allocated on the first device, and the other ones wouldn't have access to it. And then here's a couple of calls that say device reduce sum and device scan inclusive sum. These are probably reductions across blocks. Well, you have to say what device you're doing that on. This is simply a kernel launch. If you're going to launch a kernel, you have to say what device you're on. Here's another kernel launch. And this is a synchronized. That's if you want to put a blocking call, then you have to say what device you're blocking on. And this is another kernel call. And another device synchronized, which is just a block, a barrier, and that's it. And so that's probably all I've got for today. I appreciate everyone's time.
Yeah, thanks very much, Mitch. I wonder on either this or other projects, what have been the primary issues for you when you're going from Fortran to CUDA?
How many minutes do I have?
Only about 7. So
I got 7 minutes. I can say a lot in 7 minutes.
just a few things that be of interest. Yeah.
I'm ready to make this talk that, but the people who keep me in my cage said not to. But now that you're letting me, I can do it for 7 minutes. We're working on a project on Titan that has we did an analysis, and we found out 68% of the time was being spent on one line of code. And we looked at it, and well, sure enough, it was surrounded by 3 loops. And we said that's a matrix multiply, which is the most performant thing that you can have on a GPU. So that was good news. But then it turned out the matrices were very tiny, and so it made sense to do a batch matrix multiply, which CUDA has one of those. But it was absolutely killing us, the batch matrix multiply, which means you do, for us, we were doing about 6,000, you send 6,000 matrices at a time through this call. But the thing that was killing us was you have to do 6,000 mem copies to set this up. It's an array of pointers to matrices. And so for each element in the array, you have to do a malloc and a mem on the device and a mem copy. The latency for all those mem copies was killing us. And I wrote a little test piece of code in what I call the sandbox, not on Titan, where I demonstrated that you could set those. Because the arrays were all the same size, you could malloc that whole chunk in one call and set the internal pointers yourself, because you do the distance between them, and just make one mem copy, one memory transfer. You were still transferring the same amount of data, but we got a 280x improvement on that piece of code. And then it turned out that in the next version of CUDA 8.0, which at the time wasn't on Titan, they have a call that does that. They didn't have it for the version I was working on, but apparently I'm not the only one that thought to do that. That's one issue. Have we still got more time?
Yeah, we actually had another question come in from someone. Sure. So maybe while I'm asking that question, if you could stop sharing your screen, and we'll get Marcus Christie to share.
All right. Thanks, Nancy.
Yeah, that would be great. So our next question is from Paul Rodriguez, who has expertise in these areas. Has a question about the performance between the Bayes estimating technique versus the particle Markov chain Monte Carlo method. So I might unmute, well, actually you can unmute yourself, Paul, to kind of ask this directly so I can kind of capture the...
All right, can you guys hear me okay?
Yeah. Sure can.
Okay, so my question was basically about the 2 estimation techniques. One of them seems, the Bayesian technique, I imagine, is going to be a lot faster if it's not doing a full Monte Carlo search. And so I'm just wondering if there's a big difference in performance or a big difference in which one works better.
I did read about that. Can I possibly get your contact information and get back to you with a solid answer as opposed to just what I think? Okay. Because I did read about that. My understanding was that not the particle Monte Carlo Markov chain, not that one, was complicated and compute intensive. It was taking a long time to derive the mathematics for it were very difficult. That meant when you changed anything underneath it, you had to go through that process again. By contrast, the particle Monte Carlo Markov chain estimator did not have to be redone if you changed something underneath it, and it was not as compute intensive.
Okay.
Yeah, interesting. Yeah, Mitch,
That's-
I'll get you Paul's
Thank you.
email so that you guys can
Yeah,
Thanks,
thanks.
Paul.
Yes.
Sure. Thanks, Nancy.
Yeah, great. Great. Thanks very much, Mitch. Very interesting. Our second talk is quite a bit different. So Marcus CHRISTIE is our second speaker today. Marcus is at Indiana University. Marcus actually used to be involved in the TerraGrid program back when the Science Gateways program first started, so the early 2000s. And Marcus moved on to other things and came back to IU later, and we're thrilled to have him be part of the Gateways program once again. Sorry for the jet noise here. I can't mute myself and still talk. But the work that Marcus is talking to us today is about integration of CILogon with Apache Airavata, and then that gets used in a lot of different science gateways. So with that, I'll let you take it away, Marcus.
Okay, thanks, Nancy. Yeah, so my name is Marcus CHRISTIE, and I work here at Indiana University in the Science Gateways Research Center. And I'm involved in a few different things. I guess I should say I'm not directly involved with ECSS. I'm kind of filling in for my colleague, Sudhakar, who had a conflict, so I'm kind of a guest speaker, I guess. So yeah, so I'm involved with the Apache Airavata project. I'm a committer on that project. I'm also involved with the SciGap project, which is a Science Gateway hosting project. So you can go to SciGap and say, I would like this gateway, and we can create one for you and host it. And then I'm also involved with the Science Gateway Community Institute's Extended Developer Support Project, which is, I believe that's modeled on the ECSS project. And that EDS is a way to get some help with developing or improving or whatever you need done on a science gateway. So, so as an overview, what I want to talk about is how to integrate CILogon for doing authentication in a science gateway. The CILogon lets users sign in with credentials that they already have at their institution. Then I'm also going to talk about why the Apache Airavata project uses a open source product called KeyCloak, and what we use that for. We use that to integrate with CILogon, and then we also use it for role-based authorization, and I'll talk about how we integrated that. But I hope that even if your gateway, if you have a gateway, even if it's not using Airavata, that some of the general principles here will be applicable. So what's the problem? Well, I mean, the problem's kind of an old one. Gateways expose typically shared resources and APIs for manipulating them with a diverse set of users. So you want to be able to authenticate them, and you also want to be able to grant authorization to those users. Some you'll want to give access to accessing certain capabilities that might be different from another group of users. And in the SciGap project, this a particular consideration for us is that, you know, we're hosting multiple gateways. Some gateways have multiple clients. So some way of easing the burden of dealing with this, with all these different gateways and clients, is a problem that we're trying to solve. And particularly with the CILogon integration, what has motivated that is this recent development of what we call campus gateways. Campus gateways are a little bit different from your traditional science gateway. Your traditional science gateway is typically built around a particular science domain. It's solving, you know, meteorological problems or molecular modeling problems, or it has a specific focus. The campus gateways are basically science gateways, but they're stood up for the purpose of giving users of that institution access to that institution's resources. So here at IU, we've got the Big Red 2 cluster, and we're currently working on putting up a campus gateway here at IU for accessing Big Red 2 and some of the other cyber infrastructure resources here. So authentication. There are a lot of options. I think traditionally we've had users just create a new account on the gateway, but it'd be much better to just use an account that the user already has. And for that, we're using CILogon. The CILogon is a service that allows users to authenticate with their institution's login system. And CILogon lets you retrieve credentials for accessing cyber infrastructure. But the thing that I'm going to talk about today is their OpenID Connect interface to this federated authentication system. So, what's OpenID Connect? So OpenID Connect is an authentication protocol. It's built on top of OAuth 2, and it allows users to sign in with their own identity provider, and the user basically grants rights to the client to access some of their user information. And we'll kind of see that how that works with CILogon. Okay, so this is, if you go to CILogon, this is kind of what it looks like when you land on CILogon. You pick an institution. I've picked Indiana University here, and then you click the log on button and you log into your institution. So what does it take to integrate CILogon for OpenID Connect? Well, there's kind of 5 steps here. The first step is kind of a one-time step. There's an initial setup where you register a client. You register your Science Gateway web portal with CILogon. And the main thing you get back from that is a client ID, which is kind of a public piece of information. And then you get a client secret, which is a private piece of information that you wouldn't want to leak out or anything. Then to actually log in the user, what you do is you redirect to CILogon. The user picks their institution, signs in. Then CILogon will redirect back to the gateway. And when it redirects back to the gateway, it will give the gateway an access code. And you take the access code and you exchange it for an authorization token. And once you have that authorization token, you can use that to get the user's information, which is like their email address, first and last name, some very basic information like that. And this is just a diagram of what was on the previous slide, basically. So your gateway redirects to CILogon. User picks an institution, logs in, comes back. And the gateway gets the access code, exchanges it for a token, and then you can get the user information. And this is going through those, just kind of giving you a bit of the flavor of what it's like to set one of these things up. So that one-time step, that one-time step of registering a client with CILogon. So CILogon, if you go to CILogon.org, you can get to these links. So they have a registration page. It's pretty basic stuff. The one thing that you would want to put some thought into is this list of callback URLs. So when you redirect to CILogon, you tell it where to redirect back to when it comes back to your gateway. And CILogon will match that against this list of callback URLs that you've provided it to make sure that it's actually a real or a good known callback URL. So you typically have to kind of put some thought into what's the callback URL going to look like first. So then actually doing the redirection to CILogon is pretty simple. You construct a URL, and there are instructions on the CILogon website for all this. I just kind of want to give you a flavor of this. You construct the URL. In the URL, you put your client ID that you got back from the registration process. And the redirect URI, this is your callback URL. This is where you want CILogon to redirect back to when it comes back to your gateway. And the scope. So we want to gain access to OpenID information. And so from the gateway's perspective, what happens at CILogon, what institution the user picks it's not terribly important. CILogon then redirects back to the gateway. And when it redirects back to the gateway, it passes the code as a request parameter. So this access code is this long, unreadable thing here. And so what you do then is you take that code and you make so your web portal then makes a request to CILogon. So this yellow box is a web request that the portal would make, kind of behind the scenes, and make a request to CILogon, passing the code that you got, and to authorize. To authenticate with CILogon, use your client ID and your client secret. And the response that you get back is a JSON response here in this green box. And there's some other information here that I've left out, but mostly you get kind of a long access token string. And that's kind of the main thing that you want there. And then you can use that access token to get the user's information. So, the previous slide, we're going to this OAuth2/token URL. Now we're making a request to OAuth2/userinfo. Authorization here, now we're passing that access token that we got on the previous slide. And then the response that we get back, it's another JSON object. and it's just a bunch of details about the user. So this is kind of what might be returned for me. My name, first name, last name, email address. And so that's basically, there are a few other details, but that's basically what it takes to integrate with CILogon. So then for your particular gateway, how would you want to go about integrating with CILogon? There are kind of two approaches. The scenario I kind of laid out over the past few slides was kind of a direct approach. So your Science Gateway web portal is just kind of directly integrated with CILogon. It redirects to CILogon. The CILogon redirects back to your gateway web portal. But there's another way to integrate with CILogon, and that is to have a server that handles authentication and authorization for your gateway and your gateway services. And this is called an identity and access management server. And I think the main question to ask is, or the main differentiator between these two approaches, deciding between these two approaches is, you know, do you just have one gateway that you're managing, just one client maybe, or are you hosting multiple gateways? And because in SciGap we're hosting multiple gateways, it makes sense for us to use an identity and access management server. So what are the advantages? I mean, why use an identity and access management server? Well, one thing is that we can set up CILogon once. We can basically set up CILogon to redirect back to our IAM server, and then we just add a bunch of gateways to it. The other advantage is gateway client integration is done once, so our gateway clients will redirect to the IAM server, and that's all standard and set up once. Another benefit is that we get authorization services. So the thing I'll show in just a bit is that this IAM server that we're using, it has several capabilities, but the authorization capability we're using is it lets you assign and manage roles for users. And then another thing that is maybe a little bit unique to Airavata is we don't just have a web portal, we also have backend and a backend middleware service that will also need to authorize the user's request. So in that case, it needs to know, okay, where do I go to figure out if this user is authorized to access this service? So having a single IAM server simplifies setting that up. So the identity and access management server we're using is called KeyCloak. It's an open source project. It's sponsored by Red Hat, but it seems like a fairly open source project with lots of contributors on GitHub and merged pull requests. And one thing that's nice about it is it's multi-tenanted like Airavata. So in one KeyCloak instance, we can add multiple gateways and configure them differently. This is just a screenshot of the admin console in KeyCloak. So if you wanted to add CILogon, you would add it as an identity provider, and then you fill in a few details. So the authorization URL, the token URL, the user info URL, and we kind of saw those earlier. And those would be the same for like everybody. What's different on a client by client basis is the ID and secret that you enter here. Okay, so then how do we, how would you integrate with KeyCloak? Like I said, it's multi-tenanted. They have this concept of realms. So what we do is we create a realm for each gateway. And we can then set up a CILogon for that gateway. And we can set up other options too if we want to allow the user to have kind of a local account, like in the more traditional, create a new account type scenario. For authentication with KeyCloak, it's just OpenID Connect, just like the examples I was showing earlier. It's just that you would redirect to KeyCloak, and you would call KeyCloak's token and user info services to get information. And then KeyCloak also has a REST API, and we can use the REST API to manage what roles a user has. So,
Marcus, we have a kind of a related question here for you. Can a single user go across multiple realms in KeyCloak?
That's a good question.
They're users of different gateways, I guess.
Yeah, I don't think so, but I'm not 100% positive. I think the realms are kind of fenced off authentication areas, so I wouldn't think so. You could, I mean, maybe it's obvious, maybe it's not, but you can use CILogon with multiple gateways, and you're signing. I could use, if I had an account with several gateways and they were configured to use CILogon, I could log in to all those gateways with my IU credentials. So I'm guessing that the question is about like a local account created on KeyCloak, and I would say probably not, but I'm not 100% sure.
Yeah, you could unmute and ask directly if you want to, Mona, if that captured it.
No, that was great. Thank you, Marcus.
Great, thanks.
Okay. Yeah, so this is just a screenshot of our Airavata's, we have this web portal we call PGA, and this is the administrative screen within Airavata's PGA for managing roles. So in the back end, this will call KeyCloak's REST API to actually change the user's roles. So, so we've talked about CILogon and KeyCloak. Now I want to talk about how it all kind of comes together in Airavata. So Airavata, again, it's an Apache project. It's basically a framework for building science gateways. And it's multi-tenanted, so we can host multiple gateways on the same Airavata instance. So here's kind of a very high-level picture of Airavata's architecture. The thing I mostly want to bring your attention to is we might have, with Airavata, we might have multiple user interfaces. For SeaGrid, for instance, we have a web interface and we have a desktop interface. So we might have multiple interfaces for a gateway. And then whatever the gateway is, if it's a web gateway, it's going to make calls to an API server. And this API server basically aggregates calls to the rest of the Airavata services. So what we need to do is we need to authenticate users and authorize them here in the gateway user interfaces, but we also need to do the same thing in the API server. So zooming in a little bit, the way it works is, so this orange box is the authorization server. We used a different product as our authorization server, but right now we're using KeyCloak. This blue box here, the gateway, that would be the web portal, and our Airavata backend services is this green box. So step one is we obtain a OAuth access token, and that's what we get through the OpenID Connect process when the user logs in. And then whenever the user's doing something, like when they're creating an experiment or something, that OAuth access token is passed to the Airavata API server, step 2. So what the API server will do, or what the security manager within the API server will do, is it will first validate that OAuth token. So it calls back to the authorization server, calls back to KeyCloak and validates the OAuth token. And then it will use the KeyCloak's REST API to get the user's roles. And so for every method exposed by our API server, there's a mapping of what roles can access that API method. So that's what it's checking. Okay, so what does this look like? So I'll finish up with kind of what does this look like from the user standpoint. We set up one of these for this Accord project, which is kind of a consortium of several Virginia institutions. So you can see how something like CILogon would be appealing in this scenario where you have users coming in from several different institutions. So here the user would click on login, and then they're taken to a KeyCloak login page. And this is the default skin for KeyCloak. This can be customized so it looks more like the style of your gateway or whatever. So the user has a couple options, but in this case, we'll click on CILogon, and we're taken to the CILogon page. We'll pick our institution. I picked Indiana. And so I get back, it redirects back to the portal. Now I'm signed in, but I can't do, so the way we set it up, I can't do anything. On the first login, the user is assigned a default role. We call this role user pending, but it doesn't really mean much other than it's just a bucket, and the gateway admin will get an email, hey, you've got a new user, and the gateway admin can then come in and assign the user to an appropriate role. If the user's going to be an administrator for the gateway, then a gateway admin might assign that user to the admin role. If they're just a regular user, they would assign them to the gateway user role. And once that role is assigned, then I have access to things within the gateway. So this role gets used on the front end by the web portal to hide and show functionality based upon your role. So we don't show admin capabilities to non-admin users. But then it also gets used by the API server, just like I was discussing on the diagram a few slides back. And I think that's it. So any questions, and feel free to email me also if you think of any questions later.
Yeah, thanks very much, Marcus. This is Nancy. Yeah, on the main Symposium website, there are contact links for both of the speakers. So if you come up with any questions afterwards or want to talk to them about another project that comes your way later on, you can find all the links to all the speakers for the Symposium on the website. I was going to ask about, so what you mentioned cgrid, are there other gateways that are tenants of Apache Airavata and using CILogon?
Yeah, so this is hot off the presses. This is work we've been doing very recently. So no, we don't have anybody using CILogon yet. except we set up, kind of for a demo, we set up this portal for this Accord project. But it's something that we're expecting to roll out over the next month or so. It's something that's very, it's something that there's high interest in this from the campus gateways that we're working on right now, like the IU one. It kind of, I think we still need to figure out what we're going to do with Cgrid as far as CILogon goes. So one of the things that KeyCloak can do that we haven't fully investigated is it can do account linking. So some Cgrid users are going to just want to use their local Cgrid account, but some might want to use CILogon, and how would they link those two? So there's still some open questions there.
All right, great. Yeah, there's a couple of other questions that have come in from the audience while I was asking mine. Mitch asks whether or not the web app can use the gateway to submit a job to the supercomputer, then get results back to display on behalf of the user. I think this is our whole community account model, Mitch, where someone logs on to the gateway, the job gets run on the supercomputer with the community user, and then transferred back to that user's space on that gateway. You can feel free to unmute if kind of that didn't capture the workflow.
No, that's what I was looking for. Thank you.
Yeah, this is a standard. We've been doing this for probably about 10 years now, where we're able on the NSF machines to have this concept of community accounts and then web applications with separate logons and manage jobs for the users. David asks about the experience with both OAuth 1 and OAuth 2 and how those compare.
I don't have any experience with OAuth 1. So can't really comment on that. Sorry. I think it seems like OAuth 2 has kind of taken over, but and it seems pretty easy to work with.
Do you want to unmute, David? Are you considering a change from OAuth 1 to 2?
Well, I'm using OAuth 1 just because the application I'm using only supports OAuth 1 at the moment for CILogon. But speaking with the CILogon folks, they say, well, this is legacy. Why don't you write your own, authorization thing for OAuth 2? And they say, well, I can do that, but I'm not sure I'm comfortable in doing it. And so I was wondering, if you tried both and can say, yes, OAuth 2 is definitely better, because then could have been something that would have maybe pushed me to do that.
Yeah, I can't think of an answer to that, except that seems like where the industry is moving, is in that direction. So, and it's, I don't know. What I found is that there are a lot of libraries and plugins, or whatever they're called, that make it pretty easy to integrate OpenID Connect or OAuth 2 into whatever web framework you're using.
Have you guys been using OAuth 2 for some time, Marcus?
Yeah. We've the Airavata project has been using OAuth 2. I'm not quite sure how long. We were using a different product as our authorization server. It was a WSO2 identity server, but we ran into issues with integrating it with CILogon. And that's kind of prompted exploring